4 people so far. All right, so here we go. I'm going to kind of get into this so that you guys can get into the practice here at the end of the period. If you didn't finish the lecture questions, just you can close your laptop. You can come back to them, all that kind of stuff. If they close on you, I can always reopen them. But let's get into these notes because this is a challenge. This is what makes chemistry. Okay, we're talking about endothermic, exothermic, entropy, and spontaneity. And that can get rather confusing. The other thing that is at our disadvantage is the way that this unit usually goes is we do a lab, we take some notes. We do a lab, we take some notes. We do a lab, we take some notes. And we do not have that capability right now. So I'm going to be talking about things that are hot or cold and all this different kind of stuff. And so it's probably you're going to need to kind of stay inside your head to kind of understand what's going on. Okay. But with that said, we're trying to modify one of the labs so that you can do it on Thursday. So some of this stuff will make connections on Thursday. Those of you at home will do it next Thursday. Sorry, it's like a week behind, but we're doing the best we can. So this content, you got to stay with me. And if you have any questions at home, please, please, please let me know. Okay, so this is tough. All right, so the first thing we have to define is what's called the system and what's called the surroundings. So I'm going to do a little chemistry experiment up here. I'm going to take some baking soda. This is super simple. Baking soda and vinegar. What happens when you put baking soda and vinegar together? We make bubbles, correct? So what I wanted to just point out is the actual chemicals doing the reaction. I'm talking about the baking soda itself and the vinegar itself reacting together. That is called the system, okay? The system is the chemicals or the reaction itself. The chemicals or the reaction itself. Beautiful. Okay. And then the surroundings, because we're going to talk about this a lot, and it seems very simple, but it's kind of hard once we get going. The surrounding is everything else outside of the actual chemical reaction. So I'm talking about the air inside the beaker. I'm talking about the beaker itself. If I had put this thermometer in to the reaction, this would actually be a surrounding, okay? The actual reaction itself is a system, and it affects the surrounding, which would have been this thermometer, okay? So I know it kind of seems really simple, but if you were doing the lab that we're going to let you guys do is called the chemistry in a Ziploc. The reaction, and sometimes people write RXN, the reaction is the system, and when you put your hand on it or you feel it or you're touching it, okay, this is the surroundings. We're talking the bag, the thermometer, your hand, the air, everything outside of the actual reaction. Okay? Perfect. Everybody's on the same page for that. Here we go. So we're going to talk about 2 terms. You probably know the prefixes. If you're exiting a building, are you going in the building or out of the building? You're going out. Thank you. Right? You're leaving. So the first thing we're going to talk about is an exothermic reaction. So go ahead and write that there. Exothermic reaction. And in an exothermic reaction, it's really easy. They break it down for you. Exo means out, and thermic means thermal energy. So or we can say heat. So in an exothermic reaction, the energy is leaving the system. Okay. You do have to know, so we can write that here, and thermal energy is released or going out. Okay, now, commonly, it will feel warm to the surroundings, but that is not always the case. I like to just point this out, and we're going to give you an example today of where it's not. It may not always feel hot. 9 times out of 10, your surroundings will get hotter, okay? But you can't always say that. So my good example here, and I think it has on here, boop, an example would be like a fire, okay? If I put my hand near this candle, I can feel warmth, right? So the system, which is the candle, is releasing energy, and you can feel it. This is an exothermic reaction. It's releasing heat energy. So when you got to look at this on a graph, okay, the reactants, or remember, the reactants are the things you start with. The reactants have more energy than the products, which is what you end with. The reactants, and here's your graph over here. So what you're going to really focus on is that this is higher, and the products have less because this is energy and this is the reaction. You start higher and you end lower. What that means is if I would draw anything on mine, draw a little arrow and say it releases energy. Okay, you start with more energy than you end up with because you heat up your surroundings around yourself. Awesome. I have a heat pack here, and we will talk about this heat pack in a second, but I'd rather just kind of get some notes down so that we could do this one piece at a time. My heat pack. All right. Okay, so that is exothermic. Another just little hint, we'll talk about this really quick. Both of the graphs have this big spike. We're going to talk about this spike a little bit later. It's called activation energy. We can talk about it later. But so when you're looking at graphs for endo and exothermic, you're really looking at how much energy you start with and how much energy you end with. And if you release it, you'll end up having less. Okay, this spike will be there, and we'll talk about it more some other time. If you don't release energy, that probably means you take in energy, which is endothermic, like an endoskeleton or any other endo words you can think of. Endothermic. Endo means in. Thermic means heat. You're taking in heat energy, and that is when thermal energy is gained or goes into the reaction. This is so hard because students want that to mean that it heats up, and that is not true. What it is it's taking in energy to make bonds. Okay, so it's removing energy from the area around it, cooling the area around it, and it's not keeping it as thermal energy, it's making it into something else. So everybody understands if I put my hand next to a fire, which is exothermic, why it's getting warmer. The hard part that some students have is when it takes in thermal energy, why it's not getting warmer. Okay, so we're going to keep all that kind of good stuff. It might not always feel cold, okay, but more often than not, if you get a decrease in temperature around, that means you have an endothermic reaction. So we have this ice pack thing we'll talk about in a second. Have you guys ever seen these? They have ammonium nitrate crystals inside of them and a little bit of water. You pop this, and then all of a sudden it gets really, really cold, and you can put it on any injury that you have. Okay? Perfect. All right, so let's talk about the graph. Oh, you know what I meant to do? This graph up here, friends. Write exothermic on it, just so I know it's right next to it, but that doesn't hurt. This is your endothermic graph. And in your endothermic graph, your products, which are at the end, have more energy than what you're starting with. So now you can see you start low and you have more energy at the end. So we can say gains energy. And please note that this is not gaining thermal energy. It's not getting hotter. It's just gaining energy. Okay, and like I said, we're going to do a few more examples of this in a minute, and we will do more examples of this on the lab. But I just want to get the notes out of the way and then do some demos. Okay, so again, endothermic, you have more energy at the end. Perfect. Now we have to talk about something called entropy, and then we'll do spontaneity, and then we'll practice. Entropy, another word for entropy is disorder. If something is disordered, is it neat? No. Is it organized? No. Are things randomly all over the place if it is disordered? Yes. Okay, so you have to think about what that term means. Entropy, the true definition is the measure of the randomness of a system. So we're talking about, is everything nice and structured, or is it like crazy pants all over the place? Okay. The more disorder you have, the more entropy you have. So if you're low entropy, you're very ordered. If you're high in entropy, you know, you're crazy. I often say, if your room is very messy, who here has a messy room? You're like, I can admit it. I'm a mess. That's fine. I know where everything is. That's the quote. But it's a mess, right? So you would have a high amount of entropy. If your room is messy, you have a high amount of entropy in your room. Anybody in here like crazy, like everything has its place, put it back, that goes there, not me too, I'm on that one, okay? I would have a very low amount of entropy. I am in not a lot of disorder. I mean, I feel like I have a lot of disorder in my life right now just because of everything that's going on. But at the end of the day, if you kind of think about it as like some bricks, this would be low entropy or low, let me write and then talk, or low disorder, okay? And the pile of bricks was just a mess. That's high entropy, okay? Perfect. Let's put it all together, and then we can do some practices because we got to talk about spontaneity. Oh, we're going to talk a little bit more about entropy. Just kidding. In entropy, we have to talk a little bit about what is low entropy as far as matter goes and what is high entropy. Right here, you can see we have a solid, okay? Particles move in place, but they don't slide around. Then you can change it to a liquid where particles can go wherever they want, woo, hanging out. And then you have a gas. Which one do you think is the highest entropy? Is that disordered? No. Is that disordered? Yeah. Okay. There is one that we got to throw in there because it's chemistry, but let's kind of talk about that. I just wanted to put that in your mind here. There are 4 levels of entropy in our understanding of chemistry. We are going to start here at the least disordered or the lowest entropy. And then we're going to move to the most disordered or the highest entropy. Okay, that's how it's going to go. The lowest disorder that we can have in this class is a solid. So I want you to write solid. You will note that in a chemical reaction, if there is a solid, it will have a little S in parentheses next to it, okay? So solid. What I want you to do is just take your pencil, and I just want you to make a grid of some dots. They should be in order. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Nice and ordered, okay? Solids are low on the disorder scale. And again, talking about our little simulation here. So you'll draw a little something like that, okay? Ordered, low entropy. Everybody where they're supposed to be. You want a pencil that's purple? I'm going to go to this drawer. This one got purple pencil, okay? So everything is organized. Awesome. The next thing that you can have is you can have a liquid. In a liquid, they're still pretty close together, okay? But they're going to slide around each other. Sometimes one might take off and become a gas, but they're moving and shaking. Things are a little bit more disordered. So the next one is going to be a liquid. You will know in a chemical reaction if it's a liquid because it will have a little L next to it instead, okay? In the little box, I don't know, I kind of just drew a little container and then draw some dots. Now they're close together, okay? They're just not lined up. They're not super duper duper organized. Okay, awesome. Now you're like, well, wait a second. If that's gas, then what's this one? And some of you know about plasma, which is the 4th state matter. We're not talking about that. We're actually going to throw something in between liquid and gas. in chemistry, we took a minute last unit to talk about this thing. And what we're going to talk about now is we're going to talk about we're going to add in a solution. From the outside, you have water. And then when you put something soluble in there like salt or whatever, it goes in and it dissolves. But when you're thinking about disorder and how crazy and random stuff is, you got to kind of look inside. So if I were to show you what sodium chloride would look like once it goes into the water on a molecular level, you see that sodium and chlorine, now we have green things running around and purple things running around. And then this is not showing you, it actually has the water running around as well. So here's your water running around, and I'm going to put salt in there. And so now all these things are running around. It's just a crazy mess. If you had just said, okay, this is the disorder of water, okay, everybody's kind of moving around doing whatever at once. Once you add something into a solution, it gets even more crazy because now we have a whole bunch of things hanging around in there. So before we get to gas, we're going to do this thing we talked about, which were called aqueous solutions. That just means something is dissolved in water. And you're going to be able to see that in a reaction when it says AQ. So that just means something is dissolved in water. Perfect. So it's a little bit more disordered. Because now not only, it's like if I had you guys like run around doing whatever, and then I like release like 20 toddlers, and then they're like also running around. It's like too much in one spot. Okay. Then the last and the highest, nothing will beat it. The highest entropy that we have is a gas. And when we're talking about on the entropy scale, gases are incredibly hot. I mean, they are disordered. These molecules go wherever they want, do whatever they want. They have no structure. Okay, they're like teenagers. I don't know. Kidding. Gas is your, oh, I forgot for my aqueous solution what I would draw. I would draw exactly what you drew with a liquid and then just draw something else in it. Draw exactly what you drew for the liquid, but add something else in it to make it a little more disordered. Okay. Awesome. And then in a gas, you're drawing these, they're going wherever they want. They go up, they go down, they go left, they go right. It's all kinds of crazy. And again, you will know that it's a gas in a chemical reaction because you will see the little G. So when I'm asking you, what is the entropy doing? If you see that it starts as a solid and it ends up as a gas, you'll tell me the entropy is increasing. If it starts as a liquid and you freeze it into a solid, you'll tell me the entropy is decreasing. Okay? Just to kind of give you a hint, and I am making up these numbers mean nothing. But if I could put these on a scale of 1 to 10, least disordered and most disordered, I would give a solid a 1. Okay, very ordered. I would give a liquid like a 3. Pretty disordered. I would give an aqueous solution like a 5. And then I would double that. A gas would be like a 10. If you're ever wondering which is the most disordered, the gas 99% of the time is always winning. Very, very disordered. Okay? All right. So now, this is what you're going to explain to your parents. You're like, well, listen, I go ahead and I clean my room. And then all of a sudden it's in a high state of entropy again. That is because nature tends to favor reactions that have high entropy. Nature loves disorder. You organize your room, it's a hot mess. You clean out your folder, it becomes a hot mess. Okay? Nature prefers chaos. Nature prefers disorder. Does that make sense? Okay, so now we have two pieces. This thing about thermal energy and this thing about being increasing or decreasing entropy. We need to put those together and define what spontaneity is. Okay, so again, back to my little reaction here. I'm putting some baking soda in here and I'm putting some vinegar in here. Do I have to do anything to those things to make them react? I put them together and they just react, correct? Am I doing anything to that candle in order to make it react? It's just going. I have a piece of ice. Ready? Is it going to melt?
Yes.
I'm not doing anything to it. All of these are examples of, because spontaneous, the word to some people mean like willy-nilly or whatever. Spontaneous in chemistry means it's something that's happened without ongoing help. Okay? So it is a spontaneous process is one that occurs without any outside help. Spontaneous means it just goes by itself. The candle, once it's lit, burns. The baking soda and vinegar just react. Okay, and the ice cube melts. It is happening without any outside help. Or you can think it happens on its own. You can give it a little energy to start it. It's just whether or not you have to maintain it. Do I have to keep stirring it? Do I have to keep lighting it? What do I have to do? And this is where things can get really hard. And this is where your quiz on Friday is going to be a challenge, but we're going to work on it. We're going to be okay. In order to have a spontaneous reaction, you need to have one of the two things happening. You either have to be exothermic. Or you have to abide by nature here and start low and move high. You have to increase your entropy. That means you become more disordered from your reactants to your products, or the beginning or the end. So in order to, if I ask you, hey, is this reaction going to be spontaneous? You would need to look and see if it was releasing energy. So I guess we can write that here. You want to write that in the box? Let's write that in the box. Releasing energy. Or more disordered. Okay? Boom. And on Thursday's lab, we're going to try to do some more examples of this stuff. Okay? All right. Here we go. You must have one or two of these in order for something to be spontaneous. Something will be spontaneous if it's exothermic but decreases in entropy, that's okay. If it's endothermic but increases entropy, that's okay. If you have one of these, your reaction is going to be spontaneous. So let's do a couple examples together, and then I'm going to turn you out to your notes, and then I'm going to let you do some practice on your own, okay? So we have the burning candle here. This is how it'll always be on a quiz, test, assessment, worksheet. It'll give you these prompts. Is this burning candle burning by itself? Yes. So we know that that is spontaneous, correct? Now, we have to pick one of these two things has to be happening to match in order for this to be spontaneous. When I put my hand near it, do I feel thermal energy on my hand? It feels hot. So the reaction is releasing thermal energy. So that means it is going out. Thermal energy is going out. So is that endo or exothermic? Good, beautiful. Okay. Let's talk about a candle, shall we? It starts as a solid. Okay, and you can find here. So I usually circle. It starts as a solid. My candle starts as a solid. And now what do we have? What's this wax turned into? A liquid or even aqueous solution. Either way, it goes this direction. Is that increasing or decreasing my entropy? It is increasing my entropy. Now look up here. Do I have both things correct in order to be spontaneous? Oh, I do. Okay, so if I asked you, why is this burning by itself? You would say, well, that's because it's exothermic and increasing entropy. Duh, right? Very good. Now you're talking like some real chemistry students here. Now let's show you one where maybe it isn't always the same. And then I'm going to let you practice a little bit. The ice cube melting. It's already doing its thing here. As you can see, the ones I already pulled out here. Oh. Is the ice cube melting on its own? Yeah, Just put it there. It's melting. So is the ice cube melting a spontaneous reaction? It is. Which one do you want to do first? The easy one or the hard one? Let's do the easy one. Let's talk entropy. This ice cube started off as a solid. And once it melts, it goes to a either liquid or aqueous. It's probably tap water, so it has stuff in it. That's fine. Either way, what is the entropy doing? The entropy is increasing. Now, here's the problem. Let's talk about energy. When you have an ice cube, and we're thinking about yesterday's stuff, okay? When you have an ice cube, is the ice cube warmer or cooler than you? It's cooler than you. So the ice cube is going to be low in thermal energy compared to the outside surroundings, right? The outside surroundings are going to be high. Like if you touched it, you're hotter than it. So which direction is energy going? Is it going in or out? Everything goes from high to low, so it has to go in. In order to melt that ice cube, you have to give it energy. Does that make sense? You have to make the particles speed up. You have to be able to turn it in from a solid. You have to give it energy like heat. Okay. And as you give it energy, now it can turn into a liquid. Okay. So we're giving it energy. If energy is going in, that means it is endothermic. So looking at my two things that are kind of at the top off my screen, why is that ice cube melting by itself then? Just because of its entropy, okay? So it must be spontaneous due to the fact that it is increasing its entropy. Does that make sense? Hopefully we're feeling good here, okay? This stuff is kind of tough. So what I want to do, and we have a whole lot more examples in this packet, and I think I still have 15 minutes left, 11. Okay, I'll take it. What I want you to do is turn to Thermochem Notes worksheet number 1. And I also want you to bring up the your lecture questions. And I want you to kind of do both of those right now. I want you to do the lecture questions, and then I want you to work on this worksheet. What I think I'm going to do is we'll pick up with this worksheet tomorrow and see kind of, I'd like for you guys to be able to do these. It says, please label the following graphs as exothermic or endothermic and then explain. So if the reactants have a little bit of energy and I end with more energy at the end, does anybody remember what it's called if I take in energy and I have more energy at the end? Is that endo or exothermic? Endo. You're taking in energy. Very good. Okay. Takes in heat energy, more energy at the end. So go through. Then in the second part, you'll go through and you'll say, all right, melting an ice cube. And you can look down here if you would like. We kind of just did this one on your practice, so maybe I'll do another one. Dissolving salt in water. I'm going to do the second one down here. When you have salt, it starts as a solid. When you dissolve it, and yes, I can help. Give me 1 second. When you have a solid and then it goes into water, okay, it turns from a solid into an aqueous solution. So dissolving salt in water, does that increase or decrease entropy? It's going to move this way, so it's going to, maybe we'll label this, more entropy, less entropy. Wonderful. Okay, so if I have my solid salt and I dissolve it in water, what's happening to the entropy? It is increase. Very good. Okay, awesome. So I'm going to sit down, have a conversation over here. Yes, talk to me. Oh, is it plugged in?
Yeah, it's fully charged. It's not letting me.
It's not letting you type. Do you have like the locked keyboard on or something? All right, so I want to see you guys. I want to see you try some of these. These are very, very tough. At the very bottom here, it's even easier because it tells you what's happening. If you take a look here at this line, we have a solid and a gas going to a gas and a gas. So that means I have a solid and a gas going to a gas. My entropy should be increasing. Okay, so I want to see you finish the front of this worksheet and finish lecture questions. I'm going to come around in just a second. So let's do this. All right, Kayla, talk to me. I'm going to turn my camera so I can face you. How you doing?
Good.
Good. Let's see. What's confusing you?
Like the entropy stuff.
Okay, so entropy is just a matter of order, okay? So if you can see your item and you can see that it's a solid, that's low entropy. And then as you move from a liquid to an aqueous solution to a gas, it's getting more disordered or more entropy. So let's take a look here at this one. Melting an ice cube, okay? You have an ice cube in your head there, Kayla?
Yeah.
When you start, is an ice cube a solid, a liquid, an aqueous solution, or a gas? An ice cube.
A solid.
It's a solid, right? So we're starting there. When you're done with the ice cube, is it a solid, liquid, aqueous solution, or a gas?
Liquid.
Yep. So we go this way. And per our notes, when we go up this way, we become more disordered, or we have a higher amount of entropy, right?
Yeah.
So this one would be more disordered. Okay. Let's try one that might go the other way, shall we? Let's go across here and we're going to say, all right, freezing an ice cube. So you take some water, which is either liquid or aqueous solution, depending on, we'll call it a liquid for ease of things. So when you take liquid water and you put it into the freezer, when it comes out of the freezer, what is it?
A solid.
It's a solid. So now we're not increasing entropy. We are becoming less disordered.
Okay.
Okay, boiling water. I'll finish it off with you if you'd like. Boiling water. What is boiling water? Before it boils, water is what? A solid, liquid, an aqueous solution, or a gas?
A liquid.
Okay, liquid. And once you boil it, does it turn into a solid, or does it turn into an aqueous solution, or does it turn into a gas when you boil water?
A gas.
All right. So are we becoming more disordered or less disordered?
More.
More. Good. This last one's a little bit confusing, so we'll do it together as well. If I have a can of pop, right? There's a bunch of stuff in pop, correct? It's an aqueous solution, all that kind of good stuff. It's got sugar, it's got food coloring, it's got stuff like that. When you open up a can of pop, what do you hear? You hear that sound come out?
Yeah.
Is that liquids coming out, solids coming out, or gases coming out, do you think?
Gas.
Yep, it is. So we go from here to here. So what's happening to the disorder? Is it becoming, remember, this is not disordered, and gases are always high disorder. So that is becoming
more disordered.
You got it. Okay, so those are a little bit harder because you actually have to think of them like outside yourself. You can also do entropy in chemical equations. So if you take a look at here, we always look at the reactants first, the products. So over here, I'm going to erase out of my little thing again. Okay, I have aqueous and aqueous going to a solid and a liquid. So that means I'm starting here with both of my reactants, and they're going to this, and they're going to this. Is that increasing or decreasing entropy if I go this way?
Decreasing?
Decreasing. Very good. Very good. Okay, so you got to think it's about how much order you have. Right here we have a liquid and a gas going to a gas and a gas. You see how I'm looking on either side of the arrow? That's the important part. How it begins and how it ends, right? So I'm
Mhm.
starting with a liquid and a gas, but then that liquid goes up to a gas. So what's happening to my entropy? Is it increasing or decreasing?
Increasing.
It is increasing. And I'll let you hit this last one here. I have a solid and a gas, but then and you have to look around the sides of the arrow. Boop. That gas goes to a solid. Gas to a solid. What's happening to that entropy there, Kayla?
Decreasing.
It is decreasing. Okay. So you kind of just got to practice some of those. And we can actually, you know what, if you guys can get just the front done, which I kind of just did with you guys, get the front done. We'll do the back. We'll do those as demonstrations starting tomorrow, because then we got some tough other stuff going on here. Perfect. All right. Did everybody get their lecture questions done? Lecture questions done. Here, let me talk. All right. Anybody else here still have questions? I'll be right back. Those of you, 1, 2, 3.